The next speaker I'm delighted to introduce is Daniel Muthukrishna, who's originally from Down Under, from Australia. Did his PhD at Cambridge and his postdoc at MIT. We've been working together for many years on anomaly detection for optical time series data. And he's going to give a very technical and very serious professional talk, as you can tell from the title, From Squiggles to Signals. Thanks, Dan. Take it away.
Thanks, Michelle, and thanks for having me here today. It's great to be back in the UK, in Oxford. So, as Michelle said, I'm Daniel Muthukrishna. I'm a postdoc at MIT, and I work a lot on astrophysics and time series data and seeing how we can apply machine learning to this. And I guess the ultimate anomaly, as Michelle's mentioned, would be the SETI signal. All right, so astronomy's reached this pretty incredible time, as we've had, right, where we have more data available to us now than ever before. And upcoming surveys, such as this Rubin Observatory, are really going to change the game a little bit. It's going to observe over 1 million alerts every single night, right? An order of magnitude more than any survey to date. And I think as such, new and novel approaches are necessary to be able to process and classify and find anomalies in this data set. So one issue we have here is that some of the greatest discoveries in astronomy have largely happened serendipitously, have happened by accident, right? We've heard already from Jocelyn Bell, and when she discovered the first pulsar, at least I read this on the internet, I have to confirm with Jocelyn later, she described it as an unclassifiable squiggle, right? And that really was an anomaly, right? She ended up creating an entirely new field of astronomy where you have these rotating neutron stars that create this lighthouse effect. And at the time, I was speaking to Chris Lintott yesterday, he mentioned that they originally thought this might have been the first techno-signature, and Jocelyn was quite upset by this because it meant she had to rewrite her PhD. But in fact, more and more in astronomy, we've had discoveries that have happened largely by accident, right? From the first exoplanet discovery, right, which was 51 Pegasi b, discovered by a PhD student at the time, T.D. Kellos, no one expected hot Jupiters to exist, right? No one thought that a Jupiter-sized planet close to its star would be something that was common. And yet now we find that that is the most commonly found exoplanet in the universe. The first gravitational lensing event, where we have identical spectra observed in the night sky, right? Confirming Einstein's theories of gravity, also by accident. Fast radio bursts, again, once thought to be alien origin, happened by accident, right? It was a very, very sharp signal in a data set that really did appear as an anomaly. And so the question is, if so much of astronomy, so much of the greatest discoveries have happened largely serendipitously by accident, what are we going to do in this new era, right? So here's an animation I always like to show, which personally I'm interested in supernova, and it shows you every single supernova we've ever discovered, plotted against the night sky, since the first observation in the year 1054, when Chinese astronomers looked up and saw a new star appear in the night sky, up until about 2018, right? And it's about 13,000 events. And this might sound like a lot, right? But it pales in comparison to what we're about to find, right? LSST is going to observe over 10 million transient alerts per night. It'll hopefully start beginning observations next year. But astronomical searchers have so far largely relied on human eyes to identify what's interesting and what's not interesting. And so how do we find the needles in the haystack? How do we find what's interesting and what's not from this massive wealth of data? Okay, if there was a wow signal there, would we really have a human writing this, or would we have to have a computer to write on the side of this that they found something amazing? So we do need to automate serendipity. And so we've seen a version of this plot already, but this shows us some of the known transient universe. That's the time domain, time-changing universe. And I plot brightness on this axis versus time scale on this axis. And up until about the end of the last century, mostly what we knew about was supernovae, right? We have type 1a supernovae and core collapse supernovae. But since then, and since we've started exploring and looking more at the night sky and observing with new surveys, we've found more events. We've found 1 kilonova. Only one event has ever been discovered in 2017, and potentially more soon, right? It's a very rare and novel event. We've got novae, we've got intermediate luminosity red transients, calcium-rich transients, tidal disruption events, which are stars being ripped apart by black holes, superluminous supernovae, 0.1a supernovae, which are still hypothetical events, and gamma-ray bursts, these relativistic explosions. And all of this is to say that the more that we've looked, the more that we've found. Right? The universe is very rich for discovery. And these are just two parameters I'm plotting here, brightness versus time scale. If you consider wavelength and other parameters even more than this, we should expect that there's a lot of unexplored parameter space out there. And for the first time, we have surveys exploring completely new areas of this space, right? LSST will observe a much brighter much brighter parameter space, and surveys like the Transiting Exoplanet Survey Satellite are observing much shorter timescales. Okay, so we've had this discussion already, and it does lead to a lot of debate on what actually are anomalies. I would say known knowns are the things that we already understand, right? These are not anomalies. But what are anomalies, I think, should be both the rare objects, the things that we know about they exist, and these known unknowns, things like kilonova, where we know only one of them, they're very rare, and these unknown unknowns, things that we don't even know to exist. And the way we can test our algorithms is with these rare objects, and hopefully by applying it to these rare objects, we can find completely unknown unknowns. All right, so how do we do anomaly detection? Let's get into some of the details and some of the machine learning. Okay, so the classical approach is you do some sort of clustering algorithm, potentially the most intuitive, right? You take your data, somehow parameterize it, and you look for the high density region. Anything that's further away from this high density region, for example, these points on these red points, right, they're outliers. And effectively, anomaly detection is just a process of doing outlier detection. Okay? Another approach, which we've heard a little bit about, is isolation forests. And this is, if you've heard of decision trees, it's basically applying decision trees to your data. And if you're not familiar with it, it's basically a game of 20 questions, right? You ask a bunch of questions, for example, was there calcium in this line, or was there not? What was the flux at a particular wavelength? Keep going down this tree until you can isolate each object. If it was really easy to isolate, that's probably an anomaly, right? There was very few parameters that kind of separated it. And if it was difficult to isolate, it's probably an inlier. Okay. So what we can do is we can then apply these clustering algorithms to our data, and we can often do this with, to get some sort of classification process out of this as well. And here's an example where we've applied it to some known transient or variable star events. So for anomaly detection, I think there are really two steps. And so I mentioned the second step here, which is this outlier detection. We can either do clustering or we can do isolation forests. But I think the much harder step is step one, doing the feature learning. How do we find a feature space or a latent space or an embedded space? I'm going to use these terms synonymously, right? And what I mean by a latent space is it's some space that represents your data. So you do some sort of representation learning and you learn some sort of lower dimensional space of your data. And the question is, how do we find a latent space that is useful for anomaly detection and useful for downstream tasks? So typically, we might do some sort of feature extraction, handcrafted feature extraction. We pick out features that we think, as humans, are relevant because we're experts in this field, and we look at, okay, well, we think maybe the rise time of a supernova is important. Maybe the standard deviation is important. Maybe the mean is important. Maybe the color at a particular wavelength is important. And so we pass in all of these things that we think are relevant, and we chuck it into some algorithm like a random forest. This is not bad, but you're highly constrained by your feature set, as we heard from Alexis earlier today, right? If your feature set is biased, isn't a good representation of your data, you're not going to have a good result, right? So what can we do differently? Perhaps we can do something more general. Perhaps we can build some sort of generalized model and learn features from the data directly with the neural network. So what I'm going to try and show today is we're going to try and build some sort of foundation model, a multimodal foundation model that can try and learn some representation of the data, right? And so the analog I'm going to pass in, which is more familiar to you, is probably like ChatGPT, right? ChatGPT can predict the next word in a sentence very, very effectively using a transformer architecture. And we can do the same thing with light curves, right? We can predict the next flux in a time series. And so our time series are effectively the language, and our fluxes or our brightnesses are effectively the words. So this is effectively what we can do, is given some partial data in the gray region here, we can then predict the rest of the light curve. And this is very similar to how a transformer works when you're interacting with one of these LLMs, is you pass in some amount of input text, and it can predict future text. Yeah. And so we can do that for a time series as well, where here we've got our data in the error bars and our mean predictions in the solid lines and our posterior predictions in the baseline. Okay. So we can encode the light curves with a transformer. Maybe we can also encode some of the other physics, right? Some of the other things we understand, right? So we have a lot of systematic errors in our data. Right? One of these errors is these telescope systematics. Here I'm showing these scattered light bubbles we get caused by light entering the telescope that we don't really want to be there. Right? And they're very difficult to remove because we don't have good analytical models for them. And in the same way that DALL-E can generate images really, really nicely with the diffusion model, we can generate these scattered light images as well and generate some of these systematics. The third mode I want to talk about is images and spectra, right? So we have our spectra, which we heard in the last talk, and we have our images. Maybe we can just have a convolutional neural network that can represent these architectures. Pretty standard pretty standard approaches. Convolutional neural networks have shown a lot of success in image classification in general and image generation. So we have our three modes, and what we're going to do is we're going to pass in our three modes into some sort of joint embedded space or joint latent space. Okay? So we have our light curves, which are encoded with a transformer, our systematics encoded with some sort of other model, like a diffusion model, and our images encoded with a CNN. And what we want is we want to have some joint space that learns a representation of all of our modes of data, right? And the trick to this is we're going to do something called contrastive learning. And there's no good machine learning talk that doesn't show a picture of a cat, so here's a picture of a cat. And the idea is that we want to have similar objects, so things that are both cats, or in our case, both the same type of supernova or both the same type of object, to have a high similarity score, and so we're going to raise that up. And things that are different, like a cat and a dog, to have a low similarity score. We're going to push them away in this latent space. And the point here is we want to structure our latent space such that it learns to encode similar types of objects closer in that latent space. And this works really, really similar to a really nice paper that was recently released by OpenAI called CLIP, which is this contrastive learning approach. And the idea is that you feed in textual data and you pass in some sort of show me a picture of a cat, and it will produce a picture of a cat and vice versa, right? And it has this joint encoding where you encode both the text and the image data into this space, right? We want to do something very, very similar where we replace text with light curves, and we have our light curves encoded in one model and our images and spectra encoded in the other model. Right? And now we can go back and forth between these things, and we have a joint learned representation of both of these modes of data. Great. Okay, so ultimately, once we've done this, right, we have some sort of embedded space that represents our data, and I'm plotting this embedded space in 2 dimensions here with a manifold embedding technique called UMAP. And we have our 2 dimensions that represent all of our data. Okay? And these are all of our known classes. And in this plot over here, we show our rare classes, our anomalous classes. Right? And so what we want to do, you can see already that our anomalous classes do kind of separate away because they weren't learned about during the training phase. And what we can then do is we can pass in this feature learning approach. We're passing that feature learning approach into some sort of isolation forest like so. And then we can get our isolation forest to spit out anomaly scores for us as well. Here we can see that the common types of supernova here have much lower anomaly scores than the rarer types of supernova over here. Okay, so the red. And so that's ultimately it, right? We can do this. We have these 2 steps. We have some sort of feature learning that represents our data, and then we can do some sort of anomaly detection. So I'll conclude here and say that a lot of discovery in astronomy has been driven by serendipity, and a key goal for us is to automate this serendipity. We need to learn some sort of feature space that is useful for anomaly detection. And one really nice way to do that is to encode all of the data that we have available into some joint space and let a neural network learn this joint space really, really well and structure it in a way that puts similar types of objects together and hopefully anomalous types of objects separately. So, thank you.